All right, we are live. So it is my absolute pleasure to have David Tagliamonti here with us. He is a staff software engineer at Ambient AI, where he leads the Forensics product, which is an AI-powered video investigation platform. And he's going to be telling us a bit about online A/B testing of real-time event detection systems. So with that, take it away, David.
Thanks, Ben. I'll start by sharing my screen. Excited to be here. As Ben said, the topic for today is online A/B testing of real-time event detection systems. This is a bit of a mouthful, but I promise I'll break this down over this talk. One thing I'm very excited about is this is a very practical talk. So this is born out of a lot of the challenges we faced at Ambient around shipping machine learning models quickly, particularly making updates to those models and doing that in a way where we had high confidence in what we were shipping. So I hope that you find this useful, whether you're working on ML systems today or plan to in the future. A bit of a background on me, and then I'll talk about the company briefly to give a bit of context. So I was at Stanford from 2017 to 2019, doing my master's in computer science. I was doing the AI track at the time, but took some systems classes and really fell in love with systems during that time. In 2019, I started working as an applied research scientist at Ambient. It's a pretty small company at the time, about 15 people. My mandate at a high level was to work on deep learning systems for computer vision. Within a year, I was still working as a research scientist, but my focus shifted a little bit, started working on evaluation frameworks, inference optimization, data collection, experiment tooling. So you'll see this intersection of AI and systems comes back into play here. And it was during this time that I worked on the system that I will be describing today. Realized that I really like back-end work in systems, and then in 2022 formally shifted over to a software engineering role, worked on a lot of back-end projects, and most recently lead our forensics product, which is an AI-powered investigation tool. A bit of context on Ambient in a sentence: it is AI for physical security. This takes a couple of flavors. So our first and still most popular product is our real-time threat detection. This covers the full gamut from detecting a person walking around, let's say at night in front of a property where they shouldn't be, to somebody brandishing a firearm, and many, many things in between. We can detect these things live on camera streams, deliver alerts within a couple of seconds of something happening in the real world. And there's a whole dispatch flow built on top of that. You can dispatch guards, coordinate a response to an incident. The other pillar is our investigation tool. This is something I work on most closely these days. I have an example here of what we call scene search. This is one of our newest additions. You have the ability to basically hover over a video stream, automatically get segmented and classified. So here, it's an example of hovering over a car, and you can ask questions like, when did this car arrive? And it'll find the exact moment of time in the past, even if that's a few hours to a few days before when that car drove up. So some really cutting edge things there. And then the last pillar, this is more esoteric if you don't work in the physical security space. Basically, if you're, connect this back to the main audience here, if you're a student at Stanford, you have an ID card. That ID card is your access badge to your dorm, to a bunch of buildings on campus. Every time you badge into a building, those things get logged. Anytime a door is held open for too long or it's forced open, there's a bunch of sensors around doors for these things. All these things trigger alarms, and security teams will manually go through all these to basically see if anything bad's happening. As you can imagine, this is tremendously time consuming, and computer vision can help a lot here. So this is another dimension to our product. Okay, so I wanted to go through that. I think this will set the stage on the problem we're going to talk about today, which is broadly this idea of event detection. I gave some examples from physical security, but this can equally apply in other domains. In cybersecurity, you could have intrusion detection system, which is looking at network traffic to detect malicious patterns like port scans. In the healthcare space, you might have a wearable device, which is looking at your pulse patterns and detects if somebody's having a heart attack or some other abnormal event that might merit going to the emergency room. And then the really interesting systems, I think, are the ones that are real time. So these systems, instead of being based on like API style patterns where you send a request, get a response back, they're typically chained in what are called streaming platforms. Now, this is different than video streaming like Netflix. This is the idea of data streaming, where data will flow through a collection of systems. Typically, they follow the structure where you have an input queue. This could be images, it could be text. This gets ingested by some event detection system, which then emits events of interest. Now, the context of this talk and how we built this work is in the physical security space and specifically on vision, but you can imagine building these systems in a lot of other domains. So I know LLMs are very popular these days. So here's one possible application. If you have live call transcript for a medical hotline, let's say patients can call in and talk to a nurse or a doctor. Those transcripts are recorded live and sent to an event detection system. You might have an LLM or chain of LLMs which are monitoring that conversation to look for any evidence that somebody should go to the ER. Maybe the patient says, oh, I'm feeling this kind of pain or this kind of pain, and that's indicative of a stroke or some other event that merits going to the ER. So even though this came out of a physical security domain and in the video domain space, you can equally well apply this to all the latest models that people are working on today. Okay, so getting at the goal of what we're trying to do here. So we have some existing real-time event detection systems. I gave a couple of examples of those. And what we want to do is we want to be able to make updates to the logic in order to make it more accurate. So this is the idea of basically shipping machine learning models quickly. And just to drive this prior point home, this event detection logic is very generic concept. This could be a rule-based system. It could be classic ML, like logistic regression. It could be some deep learning system. It could even be that you want to just iterate on the prompts that you're making to an existing LLM. That can also be part of this broad umbrella of event detection logic. Okay, so what are some of the challenges here? The first one is that these systems are often mission critical. So in the physical security space, if you fail to detect an unauthorized entry, somebody can steal property or somebody can be attacked. Cybersecurity, we've seen a lot of these examples in recent times. Companies held for ransom, their business is interrupted for quite a long period of time. But not only false negatives, false positives can also be really bad. So if you have a medical device and it says you have, you're having a heart attack or some other abnormality, and this causes you to go to the ER when you don't actually need to, this can cost thousands of dollars as well. So a lot of these systems can be quite sensitive. And so one thing we want to do basically is make updates to these event detection systems with high confidence. So we don't want to push any kind of changes that cause a regression. And I want to amend it in the second way, which is you also want to make frequent updates. So one common solution is, okay, well, let's just go really slow. Let's have this high confidence offline, and then we can push these systems. But that really slows down your progress. And so we want to both ship with high confidence and do so frequently to be able to make a lot of updates. The second key challenge is that measuring accuracy is hard. So I'll come back to this example of detecting somebody entering through a door in a video. You can imagine in a video stream, you can take any start and end point, and it's not really well defined where you start and end. It's just a continuous stream of video. Any one chunk of that video could have somebody entering or exiting. So you can think of event detection as a subsequence classification problem. Is this event happening in this sequence of video or this chunk of a conversation? But there's no really well-defined start or end. And when you're processing data in real time, at any point in time, you might say, okay, something's happening now. And so this is very different than, say, image classification. We have a very clear input and output pair. The other one is asymmetric cost. So depending on your application, false positives or negatives can be worse. In any event, recall is usually very important. Like you want to know what percentage of real events are you detecting. And one thing that was quite surprising that we had to learn along the way is that precision is usually very misleading in these kinds of applications. So imagine you have a system trying to detect somebody entering through a door, and there's a camera just pointing at a door and nobody's there. And if you have one system that runs for an hour, and maybe there's some shadows and it thinks somebody entered, and it fires once in an hour versus one that fires 50 times in an hour, they both would have a precision of 0 in this example, but one is clearly far worse than the other. So we started using something called the false positive rate, how many false positives you get per unit of time. I'll come back to this idea a little bit later when I get into this idea of measuring accuracy. So these are some of the challenges of making iterations on these real-time systems. And there's a couple of things you might think of. So the first one is the classic ML thing, which is you build a test set. So collect a bunch of positive, negative examples of your event of interest, and then you use this as your test set before you release models. And this is a good place to start. It's usually quite easy to get an initial data set depending on the application. And it is very important for recall testing. So this is an important component of an overall solution, but it has a number of limitations. In particular, it's not good for false positive testing. And we saw this a lot in our case where we would, we have some model that has some failure modes. We train a new model to make it better. And on all our offline testing, it looks great. We deploy it in the field, and all of a sudden it has a bunch of new failure modes that we didn't previously collect data for. Now, of course, you can just collect those ones and iterate again and again, and that will improve over time. But we found consistently, it's hard to be very consistently confident unless you do the solution that I'll talk about in a bit. That said, this is still helpful for some hard examples where most models will get confused. And then finally, depending on your domain, data distribution shifts can be a problem. This is the idea that data you collected last week is different than the data you're going to run inference on this week. And to address this, you typically need to keep collecting data, and this can be quite expensive and time-consuming to curate new data sets. So even though it's maybe easy to curate an initial one, the idea of continuously curating data sets can be quite time-consuming. So if offline doesn't work, well, what about online testing? This is a broad category of testing where you basically run your model in real time on production data to get a sense of how it's performing, and you split it by input groups. So broadly, you can take one of two approaches. You can divide run model A this week and model B next week. This is called a longitudinal cohort. There's an obvious problem here, which is if there's some other reason why the performance this week versus last week is different, this skews a lot of your results. So there ends up being a lot of confounding variables in this case. The other one that works better is cross-sectional cohorts. So you can split a user group into two, and you run model A for one and model B for the other one. And this can be quite reasonable if you can randomly sample. But there's a pretty critical flaw for both of these approaches, which is you don't, especially in these very sensitive applications, you don't want to run model B until you've validated it. This approach that I'm describing here is in this online cohort testing is pretty common in things like product recommendations. So I would imagine that like YouTube's recommendation algorithm, they tested in this kind of fashion where they'll subject some small set of users to a new version of their model and see how that performs, look at click-through rate, product recommendations as well. These are lower stakes environments where this kind of thing can be done. But even there, you can read stories about, someone pushes a bad change to the YouTube algorithm and they'll lose $10 million in an hour. I remember reading stories about that a while ago. So, and especially in more safety critical applications, you typically don't want to expose users to a new model until you've properly validated it. This brings me to how we've solved this problem. So what we do is we built something called the shadow stack. And this is a full replica of the production event detection system that runs in the shadows and a monitoring dashboard to compare the outputs. And so I'll break this down. I will pull up this chart I had before. So we have here like a very generic real-time event detection system. You accept inputs, run some logic. Again, this could be machine learning models, could be rule-based systems, could be API calls to an open source LLM or a commercial one. And then you have some output that you care about that you want to send to customers. So what we do is we basically copy the event detection system and its output queue, and we run a parallel version of our code. And so the important features is that, one, it does not affect the user's experience. As far as they're concerned, they're still getting the outputs that they would get from the incumbent model. This is version A. But you run this parallel system completely in the shadows, so to speak. It ingests the same input queue. So this ingests all of the live production data, and it writes its outputs to a separate queue. So I have this as output B here. And then there's a separate system which basically writes both of these outputs to a database, and you can then visualize this with metrics. I'll get into this in a second. So this is a relatively simple setup. Basically just have a copy of your production system, run it on the exact same input, but have a separate output, and then you create systems which can then compare how these outputs run. And so yeah, these are the two key features here. One is that it's fully online, so you're not relying on offline data sets, but you're not affecting user experience. That was one of our key downsides before. And you run it on all your production data, so you don't need to select cohorts. Now there's a couple of key benefits here. One is that it's representative. So this will tell you exactly how your model will perform if you were to deploy it now. And we found that this is very, very important for false positive testing. So I gave the example before where you collect a data set of failure modes for your model, you retrain a new one, deploy it, but then it has a bunch of new failure modes that you didn't detect. These are immediately surfaced with this kind of framework. You also don't have issues of data distribution shifts because you're running it on your live data, and you have no uncertainty from cohort selection, again, because you're running on all your data. As a sidebar, one of the things I found working with ML in production is you basically want to systematically remove uncertainty. That becomes one of the main drivers for deploying models fast, is if you can get to high confidence on a new model, you end up releasing much faster, and then your service will improve much quicker over time. So having a representative test suite, this is not even test suite, but having a representative mechanism for testing your model is what leads to high confidence. The other one is that this is very easy to run experiments. The way we set it up is that one experiment is just one code branch. So you don't need to learn a separate framework for running experiments. You don't do any kind of cohort selection. It's literally these 4 commands. You create a new branch, you'll make your code changes, commit it, push it, and then deploy it to the shadow system, and you can see how it performs. And so because it's so easy, people end up making a lot more updates. The folks who are working on our machine learning models end up making a lot more updates to the logic over time. And then also really important, especially for startups or smaller teams that are just getting started, there's very little engineering overhead here. So you're just running a second copy of your production system. You don't have some third-party tool you're trying to integrate with. You don't have an experiment platform to understand. You just run a separate copy. You're working on the same code base. And in terms of like the DevOps overhead, all the monitoring, testing, deployment, support, all that is the same because it's literally the same system, just like a copy of it. With any system, of course, there are downsides, and here the main one is cost. So you are running a full replica of your production system. So if you have a lot of traffic, or if you're running heavy models that are quite expensive to operate, all those costs will get duplicated. You could, of course, modulate this. You can turn it on only when you want to run an experiment, turn it off after. That's one way to save costs. But while experiments are running, it can be quite expensive. And then a corollary to this is that because it's expensive, you're not going to run multiple shadow stacks. So you could, in theory, have like 4, 5, 6 shadow stacks. And if you want to have more experiments running in parallel, that is another benefit. But in practice, you won't do this because it ends up being incredibly expensive. And so what we do is we run a single shadow stack, and it's shared between our ML engineers. And then they'll coordinate on Slack. So you'll see a lot of messages like, hey, are you done using Shadow? I need to test my branch. But I take this as a good sign that the system is useful. Okay, and then the last piece of this is the dashboard to compare outputs. So here I'm going to get into this idea of why measuring accuracy is hard. I have on the top here the system, just to recall it. One input queue, 2 parallel systems. They each generate their own view of the world as to what events should be generated. You can then basically log all those events in the database. And what you can do is you can group them. So let's say in the example of physical security, you would group them by camera and then by a small window of time. So did event A fire an event during this period of time, and did event B fire it? And you can basically group it that way. And then what you can do is you can create this Venn diagram of overlapping detections. So things that both version A and B detected end up in this retained detections. Things that A detected but not B are over here. These are lost detections because the new model no longer detects them. And things that model B detects but model A did not, these are new detections. And it's quite surprising that like just looking at the relative size of these buckets usually helps a lot. So if you're training a new model to improve recall, let's say, and you see no new detections but only lost detections, that's a pretty good indicator that something's going wrong. And vice versa if you're trying to train a model to reduce false positives. So often just looking at these different buckets and their sizes, and then even sampling 5, 10, 15 examples from each of the lost and new detections can help a lot in understanding what's changing with the model. If you are fortunate enough to have natural labels, this just means you have some process to automatically annotate the outputs of your models. So I'll give an example here. Let's say YouTube recommendation algorithm. If you were to click on the first thing they recommend after a video you watch, that would likely be treated as a positive label. if you scroll to the first 15 or 20 and click on the 21st one, that would be a negative label for the first 20. They weren't sufficiently interesting to you. And so some applications, you have this natural mechanism to generate labels, even though you may not have an annotation team. And so this becomes really interesting when you overlay this with a previous Venn diagram. I'll walk through this step by step because it starts to get a little bit cluttered. But the first category is lost true positives. So these are basically things that the new model no longer detects, but were annotated as being accurate. And so this is really bad. This is basically indicating that you're losing recall with the new version of your model. In the middle, these are not that interesting because these are basically either retain true positives or retain false positives, but they're the same in both versions. And then on the right here, we have lost false positives. So these were mistakes of the version A, which are now eliminated by the new model. So these are typically good. And then you have this other category of new detections. Because only version A outputs get sent to the user, only these can possibly be annotated. Whereas version B, you'd have to randomly sample some examples and see what is being detected, whether it's true or not. There's one other really important category here, which is these unobserved false negatives. These are basically things that neither version A nor version B detects. And so if you look only at your model outputs, you'll never find these. And this is why recall testing is really important. And we mentioned this at the start. It's a good part of a holistic solution, but it's not sufficient on its own. But it's really important in this category of all these examples which you don't see regularly. It's especially important for rare events, which you don't expect to see that often. Okay, so what's our experience with this system? So we've been using this in production for almost 3 years now. It's kind of crazy. As I alluded to before, the system is still very much fought over, which I think is a good thing. So we have ML engineers will coordinate on Slack and someone's running an experiment at any given time. The other really big thing, this goes to the fact that we can now have much more confidence, is that this allows us to ship much faster. So this is for one of our more critical services. You can use shadow stacks on multiple services, and we do that as well. But for one of our more critical ones, we used to deploy only 1 to 2 times per month. That was roughly our cadence. We now deploy more than 8 times per month. So this is a 5x increase in our velocity to get changes into production. And we've made tremendous amount of improvements during that time because of this added velocity. And then if you look at our deployments to our shadow stack, these are basically experiments that are run. We deploy even more frequently there. This is basically on average 1 deployment per working day per month. So this lets us run a lot of experiments because it's really easy. And we're a relatively small machine learning team. So these are some pretty big wins from the system. Another really big, and this is an unintended benefit, is that we've had near zero human error production issues for our most critical services. And that's because we integrate the shadow stack in our release process. So what we'll do is we generate a release candidate. This is basically just a branch of code that you want to deploy to a service. We will always run that in shadow, even if we're not making a model change. I'll come back to that in a second. We then have these dashboards already pre-made. So you can basically deploy your service, and then the dashboard's already configured. You just log in and you can look at how it's performing, look at, okay, these many new detections, these many lost true positives, and so on. You get very quick feedback. We use another tool as part of this process called Sentry. This is a developer tool. Basically, you can integrate this with your code, and it'll detect errors and exceptions, send them to Slack. You can very quickly see if your new code is erroring out right after you ship it. Typically, there's some iteration here. So we'll run this validation. We'll see something's wrong or there's some bug. We go back, we fix it, and we do it again. And once everything looks good, then we ship it to production. And by following this process very diligently, this has helped us avoid basically almost no bugs in 3 years. One thing that's really cool here is that even if you're not making a model change, you just want to say, make some change which should make your code run faster. Or you're doing some sort of quantization, which makes your model run faster, but shouldn't, in theory, affect your outputs. This system becomes really useful because you can basically validate, okay, version A and version B have exactly the same outputs over some period of time, and that gives you confidence that you've got an efficiency gain without impacting performance. So the system becomes really, really helpful there. Some further reading. So this is a really cool talk. It's a little bit dated now. This is from 4 years ago, but also very useful. This is the same idea of shadow systems, but not in the context of A/B testing, in the context of data collection. And so Andre Carpathy here talks about how they use shadow systems to bootstrap new models and collect data sets. So I put this here, one, because it's an interesting talk, and B, to illustrate that this idea of shadow systems are relatively common, and you can use them in different domains. We've used them for A/B testing and specifically event detection systems, but you can also use them for data collection systems. And that is all I have. Happy to take any questions.
Great, thank you so much, David. Really enjoyed it. So yeah, I guess let's move into questions.
Yeah.
Do you want to start, or shall I?
Yeah, I mean, I think we've got a couple sort of, I guess, audience prepared questions we can talk about. Do you want to chat?
No,
or-
go ahead.
Okay. Yeah, so I guess I was curious, David. I think one of the really interesting things here was this mention of like sort of like real-time predictions, right? Or being able to do event detection in real time. And I was curious, like, if you could say more a bit about some of like considerations that I guess come into play there, just starting off from a very high level, right? Like versus like, I don't know, we typically think about like training models, right? We just like, train once and then like, I don't know, use it to do inference. Like what are some things or challenges that come up with like having to do with like real-time latency?
Yeah, so like I'll come back to this slide. So if I reiterate the question, what are some challenges that come about with doing things in real time?
Yeah.
Yeah, so I mean, for one, you want to typically use models that run quickly. Okay, so let me structure this answer. There's a couple of things. When you're doing like purely benchmark-based testing, typically you just look at performance on some benchmark, and you could have a model that's 4 times bigger, but it's like slightly better, and it's preferred in the research literature just because it's better on some benchmark. When you start looking at real-time systems, you typically have to make this trade-off between runtime and performance. And typically, if you're doing like a literature review, you'll look at a bunch of different possible models that you can run. You can plot them on a curve of like a runtime versus performance, and typically there's like some sort of frontier where, and also some point where making the models bigger and slower doesn't make them that much more performant. So you'll pick things that tend to be a little bit smaller, a little bit more efficient. So that's one general category. It's just like when you're looking at the models, not necessarily picking the absolute best one, but one that has a good performance to a runtime trade-off. The other thing that comes up a lot is things that are, and this is a lot more engineering work than ML work, but how do you run the system? So there's this like problem of, do you run one example at a time, or do you batch responses? So if you do batch processing, you typically get much higher throughput. So that costs you a lot less money. You can process more requests per second per minute, but you increase the latency per request. And even there's some sort of trade-off. Like you don't want to wait too long and batch too many requests because that might slow down your processing. And you typically don't want to do one at a time because that ends up just being very inefficient and costing a lot of money. So there's a lot of engineering considerations there. And then maybe one more thing, which is when you're looking at the video domain, when you're moving lots of data around, there's a lot of stuff around how do you actually move video, some things around codecs, how do you batch things? That's a whole other world. But yeah, you have to start looking beyond just the model. And like one thing, for example, we've worked on in the past is pipelining. So if you can have some things run in parallel, that can speed some things up as well.
Cool. One student asks about, I guess I'll paraphrase a little bit. When you are finding false positives or false things or whatnot, to what degree are you, relying on users to tell you this stuff versus like, do you have your own, do you do the work, yourself as a company of going and finding the errors?
Yeah, so this one, that's this chart, I think. So I'll come back here. So yeah, the way we do things, we have some feedback mechanism that doesn't just rely on users. We also have in-house annotators that will do some of this work, so we can generate labels. Yeah, so it depends on the application. For physical, for our case, we'll rely more on in-house stuff than users, but some other applications you could the user signals could be quite strong. So the example I gave of if you have a recommendation algorithm and someone's intentionally scrolling past 20 results until they get to the 21st one, They don't need to explicitly say, oh, I don't like what you've recommended, but by their actions, they've told you they don't like it. So in our case, we'll rely more on annotation, but in other consumer-facing products, you can pretty reliably use user feedback.
Makes sense. One question for me actually is, so you talk a bit about distribution shifts in terms of like how important it is to have different cohorts and like the whole reason to have a shadow stack in some ways that you don't have to do this cohort splitting. Can you talk a little bit about the kinds of distribution shifts that you observe and like why they cause so much trouble for your models?
Yeah, so that was this point over here. Yeah, so I'll talk about our case specifically of physical security and then generalize this a little bit. So the effect to which data distribution shifts affect your model depends a lot on the application domain. So I'll talk about this example I've been using of someone entering through a door. We had an initial model we used and it performed quite well. And then we get a bunch of new customers and they have all these weird looking doors. Some are glass where you can see through. Sometimes they have reflections. And in our previous data set, we didn't have any doors that look like this. And so the model all of a sudden starts performing pretty poorly on these doors and we need to go retrain it and collect a new data set. So if you rely purely on offline data sets, it looks like you're doing pretty well. But now you have all these new examples of doors that you now need to go train a new model on. So this is an example of a data distribution shift. Now, even in this case, you can imagine at some point, if you have enough customers, enough examples, you'll have every door ever seen in the world. And then that will be pretty stable over time. So in our domain, eventually, like in the long run, data distribution shifts become less of an issue because what it means to enter through a door is a pretty stable concept. But when you look at consumer products, this ends up being a way bigger impact because what makes a user click on something now or can change a lot from even week to week, month to month, what news topic is hot or what makes a thumbnail attractive. I'm using a lot of this example of YouTube, but what makes a thumbnail attractive can change based on people's tastes over time. And so if you have a model that's based on the data set, or if you're evaluating things based on a data set you collected a year ago, it's very likely not representative of what people are doing today. Some companies take this even further and they have like continuous data collection and training loops. But that starts getting pretty sophisticated.
One more student question is from a student who works on theory for multiple testing and causal inference. Could you point to any of the academic research or research areas that you find interesting and most relevant for the work that you do?
What research world does he work in?
Theory for multiple testing and causal inference.
Okay, I'm not too familiar with that. So, but point to research areas. There are things that I've looked at in the past. So we built the system a couple of years ago. I remember looking a little bit at the active learning space. I don't know if that I remember that being quite interesting. This idea of I'm gonna maybe butcher, but the idea of like active learning is collecting data or annotating is very expensive, and rather than just sort of randomly looking around to find stuff, use models to predict where you should go collect data. That actually fits quite well when you I remember we looked at this for a little while. When you look at this framework here of, I remember when we drew this diagram for the first time, it really clarified a lot of stuff. You have this whole world of things you can detect, and there's all these areas here which are not observed. And so basically this idea of active learning is you want to explore new areas where your model potentially is performing well or you have no examples. And under this idea that data collection is expensive, it tells you where you're going to get most of the bang for your buck. This is a very high level summary. It's not something I've worked too closely on, but I think that would be one of the more relevant research areas related to this talk.
I guess like, so kind of slightly related to that, I guess, but more tied to perhaps like when you're actually deploying these things online. I'm just curious, like when you, like, how do you go about, let's say, like realizing when you're like in a distribution shift? Like, is it always like sort of like deploying a model, realizing, oh, I made a couple of new mistakes, and then like from there being like, oh, it's like a distribution shift? Or like, are there ways that you can like leverage, let's say, out of distribution detection kinds of things, or like just in general, like ways to perhaps like fail like more gracefully in some sense?
Yeah, so there are like a lot of maybe like fancy things you can do about like detecting out of distribution, anomaly detection systems. What we found is that doing simpler things is usually better. just because they're quicker to set up. And so even just having, even if you don't have natural labels, like having a system that can very quickly build this kind of Venn diagram for you, would say, okay, like your systems have generated 100,000 examples and events in the last day, and here's where they fall. And then sampling like 15 or 20 in each of these buckets, manually reviewing them as an ML engineer, usually gives you very, very high signal as to what's going wrong or what's going right. If you have a lot of loss detections, you're like, oh, my model's like no longer detecting these kinds of doors. It becomes very obvious without any kind of super sophisticated system. So yeah, this may be another theme of like doing ML in production, but the simpler you can keep things, keep your models are complicated, but the simpler you can keep your operations and how you measure things, the faster you can move typically.
Yeah.
There's diminishing returns in adopting super complicated anomaly detection systems or data distribution shifts. I know there's some research in this too. I haven't looked too closely at it. But yeah, keeping it simple usually helps a lot.
I guess so also kind of related. Sorry if I missed this earlier, but like how do you, it does sound like you kind of have like this like active or like continual learning problem, right? Where like I imagine you have like perhaps multiple models in deployment, and then like sort of like I remember seeing like over time, let's say like things change or like you're in a new setting or something like that, right? But then you have like this challenge of, let's say, when you're adapting your models to, let's say, kind of like new environments or new contexts, like you have like this catastrophic forgetting problem, right? Like the models perhaps might not work on some things that you would like them to still work on before. And so like, how do you sort of like manage that? Is there like some like fancy new like continual learning or active learning research that you're looking into? Or is it kind of like simpler heuristics, having just multiple models online and being able to switch back and forth? You can share like any strategies of dealing with that.
Yeah, even there, having it's gonna sound really basic, but I think that's where it often ends up, like having just good monitoring tools. So I'll keep this, avoid it being like too big. I'll go back to the example of like onboard a new site, new cameras, and we have these doors that we've never seen before, and the models don't perform well. If you have good monitoring dashboards where you divide your metrics into how am I performing at the camera level, how am I performing at a physical site level, which tend to have similar kinds of cameras. So we'll do that. We'll have those kinds of dashboards. Having those metrics in place where you can very quickly look and see what's happening when you onboard a new site, usually very quickly will tell you something's going wrong. And that is a good indicator. Okay, we need to go collect more data. We need to go build this model. We need to go retrain this model before we go live with these cameras. That usually gives you 90% of the value that you need without a very sophisticated system. We have started building, this would be a whole other talk, but we have built data collection systems. So one thing you can imagine is if you are getting, in this context of this, if you have labels that something is false, you can build a mechanism to collect those examples and then retrain your model. So we have built these kinds of systems. A true continual learning would be that it's fully hands-off. We don't have a fully hands-off system. But we do collect examples where our models have gone wrong. We'll do a basic analysis, see like, is there some pattern here? We can retrain our models and then redeploy them. And then where the system comes in place is if you follow this cycle. So you see your models going wrong in some new domain. You collect data, ideally in an automated way based on those failures. You retrain your model. When you deploy it, you should hopefully see that it actually gets better. And then you can use the system to say, okay, yeah, we've actually eliminated, that would be this category here for false positives. We've eliminated all these false positives in our new system. And hopefully you should do that while not losing recall as well. Before we had these kinds of systems, the kind of issues we would see is we train this new model like, oh yeah, it's eliminated all these positives. Like, okay, but what's happened to recall? Or does it have new false positives when you deploy it? And when you're just sitting in a room with a bunch of engineers, those kind of questions slow you down a lot. But when you can say, okay, now look, here's the data, like I ran it on all our production data. We eliminated all these false positives and we have no impact on recall. We're good to go. You can ship models much faster when you're operating in that world.
Thanks.
2 questions from one student. First question is, how many annotations do you need before you feel confident that a new model's metrics are significant?
Yeah, so I guess it depends on the scale. I guess you can do like one of these statistical tests where you can actually look at statistical significance. The way we run things, we have a very natural like annotation framework. So we So yeah, I think it depends. We don't have a formal rule. It depends on like what we're looking at, but it's usually pretty obvious that something is going right or something's going wrong. If things are automatically being annotated, then you're basically getting all your data annotated for free. So that works, well, not for free, but you don't have to think about it. You just look at what the impact is. If you don't have natural labels, that was the first thing I started with. Usually you can, even before they're annotated, you can see the relative size of each of these buckets. So if you are training a model to improve recall and you see very little things in this mu detections, but a lot of things in the loss detections, you know something's going wrong. If you have a new model and out of 90,000 things, like there's a lot of mu detections and almost nothing in loss detections, then maybe something's going right. It's at least a good first step. And then you can sample some of the mu detections to see. So I don't have a clean, like, hard answer on that one. It's typically case by case, but you could do like a formal statistical test to see if the differences are significant. That would be very easy actually to do something like that.
Got it. And the second question is, for the event detection, have you found LLMs to be fast for real time, or do you need to rely on other approaches?
All right, that's this question slide here. LLMs can be, so we operate in the video domain, so we're not using language models, but you can use, like, language on language models are very fast. And here you get into this classic trade-off. I think this is one of the first questions where how do you think about things that you're going to run in real time? You might not use the latest and greatest model because it's going to be slower than some smaller model. That's actually not always the case. Sometimes newer models are faster, but often there's model families, like there's a 150 billion parameter model, there's a 7 billion parameter model on the low end, and the smaller model will run much, much faster with much less memory and, you know, have accuracy or performance that's like 80%, 90% is good. So whether that trade-off is okay is like depends on the application. You have to actually run it. But yeah, typically in these cases, I think some LLMs are definitely fast enough for real-time applications.
One more question from me. So I'm curious if the comparative difficulty of like detecting false positives versus false negatives or whatnot leads to a focus within the company on, for example, like minimizing false positives rather than finding new detections or something like that, whether that's something you have to sort of counteract against.
Yeah, that's a really good question. This goes to this point of asymmetric cost. I forget where I had this, but this was in the challenges here. So yeah, I think you're asking about this idea of asymmetric costs and what's the incentive to reduce false positives or false negatives. So I can answer generically and then in our context. So generically, it depends on like how this impacts the product you're trying to sell. Sometimes having some false positives is okay as long as recall is very high. That tends to be the case for physical security. You typically don't want to miss things, especially really important things. But you're okay with some amount of false positives. And some other applications that may not be the case. So you have to tune it. Typically, what you'll do is if you care about one more than the other, you can say, okay, we want to minimize false positives subject to recall constraints or maximize recall subject to false positive constraints. That'll depend on the kind of product you're trying to sell, but that's typically, you can't optimize both. And if you remember, like ML 101 is a precision recall curve. So you can change the operating point of your model, change its confidence threshold to decide if there's an event or not, and you can change the precision or recall that way. But so you can make recall as high as you want, you can make precision as high as you want based on this. Well, maybe not precision, but recall at least you can make it as high as possible. And so yeah, typically you can only optimize one subject to a constraint on the other. That's typically how we'll think about it.
Got it. All right. Well, thank you so much. Really appreciate you coming out and talking to us. And with that, let me turn off the stream.
Yeah, it's a pleasure. Thank you for having me. Good time.